Hello everyone, I hope you're doing well. So in this video, we're going to discuss Geeks for Geeks problem of the day, and today's problem is power of numbers, and it is a medium level problem. So this particular problem says that we have been given a number and its reverse. Find that number raised to the power of its own reverse. So as the numbers can be very large, we have to print the result modulo 10 raised to the power 9 plus 7. So basically, if you have been given this like integer input n as 12, you have to return 12 raised to the power 21. And the fun fact is, both of the values 12 and 21 will be given to you as input. So you don't even have to find the reverse. You just have to find a raised to the power b. And since the numbers are pretty huge, we have to print it modulo 10 raised to the power 9 plus 7. Right. So this is our whole question. And the expected time complexity is O of log n. And if you try to do it using a normal multiplication method, it will not work. You will have to use the log n method, and we will discuss how we can solve this problem. So actually, if you did not get any idea of how to solve this particular problem, then you don't need to worry. It actually involves a concept that you must have not studied before, and we are going to discuss it in this particular video, and that concept is called binary exponentiation. So if you have not studied it before, you will not be able to solve this problem without this. And it is a very simple yet effective technique of calculating a raised to the power b. Right. So we are going to study binary exponentiation in this video, but let us first see what is the need for binary exponentiation. So for example, if you are finding a raised to the power b, you can find it like a into a into a into a into a up to b times. Right. So this can be b times. So for calculating this value, you need to run a for loop for 0 to less than b, right? See, so if you run a for loop from I 0 till less than b, then you can easily multiply this a b times and you will get your final answer. But the issue with this method is what happens when the value of b is very large, for example 10 raised to the power 9. So you cannot run a loop of 10 raised to the power 9. That is where you need some other method to find the value of a raised to the power b. Now let us see how we can solve this problem and what binary exponentiation says. So basically it says that let's say you want to find a raised to the power b, right? I can write a raised to the power b as a raised to the power b by 2 into a raised to the power b by 2, right? I can further write it as a raised to the power b by 4 into a raised to the power b by 4 into a raised to the power b by 4 into a raised to the power b by 4. So you see, what I am trying to do is, from a raised to the power b, if I want to find a raised to the power b, I can find it by finding these values first, a raised to the power b by 2, a raised to the power b by 2, right? And in order to find a raised to the power b by 2, I can find it as the multiplication of these two values, right? So I am trying to divide my problem into smaller sub problems, and once the value of b gets sufficiently small, I can find it in constant time. For example, if the value of b is 1, how can I find it? I know the answer is going to be a itself. If the value of b is 0, I can find it easily because the answer is going to be 1. So what I am trying to do is, I am trying to break the problem into smaller sub problems. I am trying to represent this a raised to the power b into a multiple of two smaller numbers, and those two smaller numbers can be further divided into smaller numbers, and we will eventually reach a stage where we can easily find the value of a raised to the power b without any for loop, right? So this is the core idea of the problem, and it will be very clear to you once you see a dry run of this particular sample. So let us try to find 2 raised to the power 10. How we can find 2 raised to the power 10? So it is equals to 2 raised to the power 10 is equals to 2 raised to the power 5 multiplied by 2 raised to the power 5. How we can find 2 raised to the power 5? So we can find 2 raised to the power 5 as 2 raised to the power 2 multiplied by 2 raised to the power 3. Similarly here also 2 raised to the power 2 multiplied by 2 raised to the power 3. How we can find 2 raised to the power 2? It is 2 into 2. Right. How we can find 2 raised to the power 3? It is 2 into 2 raised to the power 2. How we can find 2 raised to the power 2? Here it is 2 into 2. And again 2 raised to the power 2 into 2 raised to the power 2. Right. So this is how you can construct a tree. Now you will see that this value is going to be 4. So I know the value of 2 raised to the power 2 is 4. This value is going to be 4 into 2, that is 8. So this 2 raised to the power 3 is 8. Similarly, this value 4 here, this value 8 here, and then again 8 into 4, 32 here, and 32 here, and 32 into 32 is 1024. So what will be the overall time complexity of this algorithm? Since we will be traversing a tree of height h, and what is the value of height h here? It will be equals to log base 2 of n, that is 10 here. So it is actually going to be 5, and it is actually 5, but I did not draw it completely. This is also going to extend it. This is going to be 2 2, and it is going to be of height 5, right? So whatever the value of n is, you can calculate it in log n, and that is with base 2. So this was all about the recursive idea of the problem, and you will see that some states are overlapping, like this one and this one. So for them, what you can do is you can do some kind of DP or memorization, and you can save the states, so you don't have to compute it again and again, right? But there also exists one very interesting method of solving this problem iteratively. We are also going to discuss this, and this is the actual binary exponentiation. The above idea was just to give you an introduction of what is actually happening in binary exponentiation. The core idea is the same. The core idea is to reduce the powers in halves, but here we are going to see a slightly different method of doing the same thing. For example, if I write a raised to the power b, right, we just discovered that we can write it as 2 into b by 2, right? This is exactly what we were writing as a raised to the power b by 2 into a raised to the power b by 2, right? I can also write it as like this, a raised to the power 2 into b by 2. It is essentially the same thing. So can I write it as a square raised to the power b by 2, right? If I know a, it is easier for me to find a square. It might not be easy for me to find a raised to the power b, but it is very easy for me to find a square, because I can just directly do a into a, right? So if I know the value of a, I can find a square. Let's say now the value of a square is equals to x, right? Now I want to find x raised to the power b by 2. Again, what I can do is I can write it as x raised to the power 2 into b by 4, which I can further write it as x square raised to the power b by 4. I know the value of x, I can again find the value of x square, right? So you see, all that is happening is essentially the same. We are dividing the powers into two halves, but the method of doing it is slightly different than the recursive method, right? Both of them are like equally good, have the same time complexity. It's just that if you do it with the recursive method, the space complexity is also going to be log n, because you need to save these powers, right? You need to save that what is the value of 2 to the power 2. Otherwise, what will happen is you are going to call all of these nodes, and it is not going to be log n time complexity. You need to save these values so that you can reuse them whenever 2 to the power 2 is called somewhere else, right? So the space complexity is also going to be log n. Now in this particular method that we are discussing, the iterative method, it is absolutely not necessary to waste any space. It will just work in over fun space. And let us see how you can actually solve this problem. I believe like you have got an idea what I'm trying to say. I'm just saying that it might be difficult for me to find a square b, but I know how to find a square, and then I'll get a square raised to the power b by 2, right? Similarly, I can again simplify it like a raised to the power 4 raised to the power b by 4, right? So this is exactly what I'm going to do, and let us see how we can solve this. But let me first write the code for this, and then we'll discuss with the help of a diagram. So what I'm going to do is I'm going to find while b. While b means while b is non-zero, right? So let me just close this bracket, and then we have if b and 1. If the value of b is odd, I'm going to do something, otherwise I'm going to do something else, right? So let's say what I do here is I set my result as result into a, right? And what I'll do is I'll subtract 1 from b. Otherwise, what I'm going to do is else I'm going to set my a as a into a, and I'm going to divide my b by 2, right? Now I can just close this. So this will be the code of binary exponentiation, the iterative one that I'm currently talking about. And there's also one more thing, that I have to initialize my result with 1. So you see, what is the difference in this particular method is, what I do, I initialize my result with 1. Now whenever the value of b is odd, let's say we want to find 2 raised to the power 5, the value of a is 2, the value of b is 5, and the value of result is currently 1, right? Let us see what happens here in this first line. The value of b is odd, so obviously I will go inside this particular loop, I will set my result as result into A. Why am I doing this? So you see, what I was doing here was I was dividing the power into two equal halves, right? This is what I was doing here. But it is not possible with an odd power. Let's say I want to find a raised to the power 5. I cannot divide 5 into two smaller halves. So what I do is I smartly write it as a into a raised to the power 4. Right. Now I can deal with this a separately and I know how to divide this 4 into two smaller halves. Right. So this is exactly what I am doing here. I am multiplying this value of a with the result. So result becomes 2. Right. And the value of b will now become 4. The value of a is as it is. Right. Otherwise what I'll do is I'll set my a as a into a. So remember I talked about squaring the value of a. Right. This is exactly that particular step. So if I square the value of a, it will become 4. B will be reduced to half and the result is still the same. Result has not changed yet. Now in the next step, b is still even. So again I am going to square this particular value of a. It will become 16 and b is going to be reduced in half and res is still going to remain 2. In the next step, b is equals to 1. Then what I'll do is I'll update the value of res is equals to res into a. So this 16 is going to get multiplied by 2. So res is going to become 32 and b is going to become 0 and a is still 16. Right. Now the value of result has become 32 and the value of b is 0. So we get out of this while loop. So you see, now we did the exact same thing without using any extra space. So the only reason I told you the recursive method was just to give you a slight introduction. It is highly recommended that for practice you can also try to implement this particular method. Just make sure that you are also storing some DP kind of thing or a memorization array so that you can save these values. Otherwise, if you don't want to use any extra space, this method is always going to work. Now a slight modification, if you even want to write less, what I can do here is while b, I can just check if b and 1. If b and 1, I am going to set my result as result into a. Right. And I can do a is equals to a into a. And I can right shift my b as 1. So this will be inside if and all of them will be inside while only. So you see, this time I wrote even lesser lines and the code is still going to work the same. Why is it so? Because if b is odd, then I am going to do this particular step and this step is occurring every time, right? And b is going to get divided by 2. So for example, the value of b is 5. If I divide it by 2, then it is going to be 2 in the next step, right? Because it will find the floor value. Now you see the first two steps that I was doing here, the first two steps will get combined into one step, right? The answer will not change because we are only updating the answer when the value of b is odd, but the first two steps are going to get combined in one step and you can try to do a dry run for this particular code yourself. It is absolutely going to work. It is absolutely your choice which code you want to implement. I've explained the first one and I'll leave the second one as a task for you. It will be like a small assignment that you have to do, and both of the codes are exactly the same. It's just that for the second code you have to write less and some of the steps might get excluded because you're doing two steps in a single one. So let me just show you the code, and this is the second code that I have written. You can also write the first code. I've written the second code to show you that this particular approach works. So what I have done is I have initialized my answer with 1 and I have also taken long here up. I don't know if it is required or not, but I just took it for like safety purpose. Like I didn't want any overflow. So you can also try setting it as int and then trying, but it is just easier to write it this way. And what I do is I initialize my answer with 1. If r is odd, I just update my answer. Otherwise, I set my n as n into n and I right shift my r, which is equivalent to dividing by 2. At the end, I can just return my answer, and let me just show you by submitting this code that this works. And also, since we had to print the answer modulo something, so that is why at each multiplication step, I am also taking mod. You see here and here, right? This is the only extra thing that you need to do for the modular part, and you will see that they have already defined modular here, so we don't need to define it again, right? So you see it passes all the test cases, and I hope that you guys were able to understand the solution. Remember, you can solve this problem by recursion. The only thing is you need to take care of saving the states as well, and you can also solve this with this iterative method where you don't use any extra space. It is highly recommended that you can set it as a template in your code so that whenever you need it, you can utilize it again. So I hope that you guys were able to understand the solution. If you guys did, then consider dropping a like on this video, and don't forget to share your thoughts in the comments, because your engagement with this particular video really helps the YouTube algorithm to understand that this video is actually helpful for you, and it will be able to reach more number of people like you who want to keep solving new problems. So I see a lot of people who watch these videos have not subscribed yet. In case you're one of them, then definitely consider subscribing. It's always free of cost, and you can always unsubscribe if you don't find the videos interesting later. Share this channel with your friends. Until the next video drops, keep coding, stay safe, bye bye.